some theory part. Right. And we go to the next part after doing this. Right. Right. People, now the theories are these. Next one. Next theories are these, people. Write down next one. Important results. These results, people, important mean really important. In past papers, you can see these results available to prove. Right. First thing is, people, this. Write down like this. Let Z1 and Z2 be two complex numbers. Be two complex numbers, right? Then, right, first one, people, we add this Z1 and Z2 and we take its conjugate. First we add the two complex numbers Z1 and Z2 and we take the conjugate. That is equal to sum of the conjugates, Z1 bar plus Z2 bar. See here, sum of two complex numbers, its conjugate. It is equal to taking separately conjugate of each Z1 and Z2 and adding them up. That's the first relation, right? Number two, Z1 minus Z2 conjugate. Similarly, Z1 conjugate minus Z2 conjugate, right? Okay. Third one, people, this, we multiply Z1 and Z2. We multiply Z1 and Z2 and its conjugate we take. Okay. Then this is equal to Z1 conjugate multiplied by Z2 conjugate. Right. Number four, people, we divide Z1 by Z2 and we take its conjugate. Then this is equal to Z1 conjugate divided by Z2 conjugate. Okay. And next one, number five, Z inverse conjugate equals Z bar, that means Z conjugate inverse. These are the results, people. These are the results, right? Okay, now we have to prove this. We should know how to prove this. The proof are very important. Then this is how we prove them, people. We can prove them like this. People, these are very important results. Therefore, you should know how to prove this. When you go to recent past papers, you can see in most of the papers, before coming to the question, the first part of the question is this kind of theory to prove. Right. So therefore, they are very important. Okay. Right. So, and remember, people, these results, if you can manage, or if you have a good memory regarding these results only, you can really work out the questions in complex numbers, and you find more easy working out the questions if you remember these theories. Okay. Right. So then I'm going to prove it like this. First one, we assume this lit Z1 x1 plus iy1 and Z2 x2 plus iy2. Okay. Here, what can you say about this x1, y1? Here, x1, x2, y1, y2, real numbers. They are real numbers. Understand, people? Right. Now, first thing I am going to prove like this. First, I am going to add Z1 and Z2 people. Then Z1 is X1 plus IY1, Z2 X2 plus IY2. Then I can first write this X1, X2 sum. Take this I out, Y1, Y2 sum. This is the Z1 plus Z2. Okay. Now we take its conjugate. Its conjugate, people, we can obtain how? Taking the sign here is to minus, no? That is how we define the conjugate. Minus I times Y1 plus Y2. Right? Let this be, people, 1. Now, secondly, what I do is I take Z1 bar and Z2 bar and we add them up, right? Z1 bar, right? Z1 bar plus Z2 bar. Right. Z1 bar is the X1 minus IY1 plus Z2 bar X2 minus IY2. Right? So there you can take X1 and X2 like this together and take this minus sign, minus I out, then Y1 plus Y2 like this. This is the Z1 bar plus Z2 bar. Okay. This is number 2, people. Then you can see in number 1 and number 2, the right hand sides being equal, right? When the right hand side being equal, the left hand side must be equal. 1 equals 2. This gives us Z1 plus Z2 conjugate is equal to Z1 conjugate plus Z2 conjugate. The result coming like this. Okay. In that way, people, we can prove this. Right. Now start the first proof, and second one also you can do in the same way. Right. Do the first one. Second one you have to do alone. Right. Okay. Come start with you. Right now, people. Right. First one is okay. We'll come second one. Number 2. Right. Z1 minus Z2. Z1 minus Z2, we can write like this, put a minus sign. Then here we get X1 minus X2. Also take this one, we get here minus, no? Then here we get Z1 minus Z2 conjugate. Right. Here we get minus, no? They will take here this difference. Z1 bar minus Z2 bar. Right. You see. Here X1 minus X2, and once I take minus I out, Y1 minus Y2 coming here. Right now, then you can see this one, right hand side being equal, then the left hand side must be equal. Z1 minus Z2 conjugate is equal to Z1 bar minus Z2 bar. That's how we prove that. Right. Now number 3. Take number 3. Take number 3. Z1 is Z2. First, we'll take the product. Thereafter, we take its conjugate. Then separately, we find Z1 bar into Z2 bar. That answer also we take, and we see the answers being equal. Right. First, we multiply Z1 and Z2. X1 plus IY1 times X2 plus IY2. Then once you simplify this, people, we get something like this, no? X1, X2, this and this when you multiply, we get minus Y1, Y2. Here, when you multiply this and this, people, we get I squared, Y1, Y2 product, no? That I squared is minus 1, right? We put minus 1 for this I squared. Then next one, what you get is, people, here. When you multiply this and this, you can take I out. X1, Y2, we multiply this and this. When you take I out, there we get X2, Y1. This is what we get for the product of Z1, Z2. Then its conjugate going to be, people, Z1, Z2, conjugate going to be, we change the sign of this to negative, right? X1, X2 minus Y1, Y2 minus I times X1, Y2 plus X2, Y1. Number 1. Correct, no? We multiply this way, we get. And now, right, we take right hand side. Z1 bar into Z2 bar. Z1 bar is nothing but X1 minus IY1 times. The other one is X2 minus IY2. This is what we get there. Now simplify the right hand side. Then we get there Z1 bar into Z2 bar. Multiply now. X1, X2. This we get minus, and this minus make plus. Right. I and I squared, that is minus 1. Y1, Y2. Okay. Next one. We multiply this X1 and this, and I take minus sign with I out. Then X1, Y2 coming. This one and this we multiply. We take minus I out. Here it is X2, Y1 now plus. Correct, no? Simple simplification. That is number 2. Then, people, you can see the right hand side here. The same. Therefore, left hand side must be equal. Right? 1 equals 2. Then you can write the result. Okay. The result I can write this way. Z1 is Z2 conjugate is equal to Z1 conjugate into Z2 conjugate. Okay, no, people, right? For the answer, right? Right. Next one. Take the number 4 people. Fourth one. Fourth one is this. First, we'll find this Z1 divided by Z2. Z1 divided by Z2 we find. Thereafter, we take its conjugate. Then the right hand side Z1 bar and Z2 bar we divide. Right. Z1 divided by Z2. X1 plus IY1 divided by X2 plus IY2. This way. Well, now what we do is first we convert this to X plus IY form. To get that one, we have to multiply the right hand side, both the numerator and denominator, by the conjugate of the denominator. Conjugate of the denominator. Right. Right. Z1 divided by Z2, X1 plus IY1 times X2 minus IY2. This way. Now here you can simplify the denominator. This is like A plus B into A minus B, right? A plus B into A minus B, right? Then here we get X2 squared minus IY2 squared. People, minus sign come in because we must get difference of 2 squares. No, the minus sign come in after this. And after that, what do we have? IY2 perfect squared. IY2 perfect squared. Once we square that, what do we get? I squared is minus 1 and Y2 squared. Then that two middle minus signs together plus Y2 squared. Right. Now we multiply like this. X1, X2 we multiply. And this we multiply. Then I and I squared, that is minus 1 with this minus sign plus sign. Y1, Y2. And next, we take like this. We take this I, X2, Y1. Right? And people, this and this, when you multiply, we get I out, minus sign we get there, X1, Y2. Then I can divide this by this by this. Then we can form it to X plus IY form, right? Okay. People, okay, now X1, X2 plus Y1, Y2, X2 squared plus Y2 squared. And people, here we get plus I, X2, Y1 minus X1, Y2 divided by this way, X2 squared plus Y2 squared. Take this as number 1, people, right? Now take Z1 conjugate divided by Z2 conjugate. Z1 conjugate divided by Z2 conjugate. Right. This is the Z1 conjugate divided by Z2 conjugate. Right. Then we have to simplify. Always people remember, whenever we find division of two complex numbers, in order to convert that to the x plus iy form, the usual form of a complex number, what we do is, its right hand side, we multiply both the numerator and denominator by the conjugate of the denominator. Understand? That's the method, right? We multiply what? Both the numerator and denominator by the conjugate of the denominator. That's the method, right? Okay, so then we can simplify in that way. X1 minus iy1 divided by x2 minus iy2. X2 plus iy2. And this is x2 plus iy2. Right? This is like a minus b into a plus b, which is x2 squared minus I and I people I squared, no, that is minus 1 plus y2 squared. This is what we get. Then here what do you get? X1, x2. This and this we get plus y1, y2. Okay, people, now we take like this. This and this we multiply and we take I out. There we get x1, y2. Right, another one more thing we have tried here, people. We need its conjugate. Right, its conjugate only we need, people. Then number one, shall I write, if I take another one step here to write the conjugate of this, don't have enough space, then what I do is this. I take of this the conjugate. I change that. Then this will be negative. It is number one. It is number one. Another one step we have to write. I change that to that. Yeah. All right. So then I take here, multiply this 2, I take minus I out. Once I take minus I out, x2, y1. Okay. And next one, we'll multiply this and this, minus, and then this is x1, y2. Then you get here x1, x2 plus y1, y2. Minus I times this one we get, no? Right, now, okay. This is number 2. Now you can see on of this 1 and 2 right hand sides being people the same, no? Right hand side being same. Yeah, for the left hand side must be equal. So 1 equals 2. 1 equals 2. Okay. Then you can write what? This equals this. Right, no? Yeah. Therefore, we divide first Z1 by Z2. and we take its conjugate. It is equal to division of conjugates like this, huh? Division of conjugates. These results are very important, people. Remember this result, and you should be able to prove this result. Okay? As long as you can remember these results, people, working out the questions very easy, and the lesson will be very easy. No theories available in the lesson. It's a new world, new operations, new properties, new concepts, new definitions available. This all together form this lesson. Then when you work out a question, people, in the lesson, this, right? You should have this all ideas. Question asking what? Question equation 1, how did it become minus I? No, I took here, we had only this, no? But I got its conjugate. This is the equation number 1 I had earlier, dividing this by this and this by this. Then after that, I took the conjugate of this. Conjugate is obtaining by changing sign to opposite. No? Haven't gone through the theories, right? Then this one I did. People, the next one, you can understand this way. Before going to next proof. Next proof, of course, people, shall I keep a little time? I take little time. Going to next one, I come back to that. Okay. All right. So then the next one I'm going to prove after the next set of proof. Right. People now think like this. When I consider this way, suppose we have a complex number, z equals x plus iy. Right. Its conjugate is this, no? Right. Now, here x and y are real numbers. Right. First one is this. Let y equals 0. X and y can be any two real numbers, people know. We take y 0, yeah, in Z. Then people, we get what? So it comes as x plus I times 0. Z equals x. Okay. Then Z bar. What, people? X minus I into y is 0, no? Then we get Z bar equals x. People, what do you understand by this? You know, when y equals 0, this complex number Z becomes x. Y is the imaginary part, no? When the imaginary part of a complex number is 0, people, the complex number is purely real. Purely real. Is that this now? Complex number, but it is purely real now. That means Z complex number is now real number. In this way, people, the complex number is purely real. By this result, we get the relation for a purely real complex number conjugate. Is, people, what? The same. Z equals x. X is like a real number 2, 3, 5, 10, like that. in real number. But in real number, we know is a complex number. When the complex number is purely real, its conjugate is people the same, right? Then when you can consider first, for example, for example, z equals 2. Z equals 2 is a complex number, but it is purely real because the imaginary part is 0. Then what is z bar according to this result? Z bar is 2. Right, people? Remember, therefore, when the complex number is purely real, the conjugate is the same. This is number 1. Right. Number 2, I take this way. So I'm going to take this way. Let x equals 0. Real part of the complex number now 0. X0 is there. Then what happens to z? X0 iy. Right. Then put that x0 where here. And z bar 0 minus iy. Z bar minus iy. All right. What is that result, people? That result is when the complex number is purely imaginary. You know, when the real part of a complex number is 0, the resulting complex number is called as purely imaginary complex number. If you have purely imaginary complex number, people, its conjugate can easily be obtained. How? Multiplying here, this complex number is iy. Now, its conjugate going to be, people, multiplying this iy by minus sign. Then when the complex number is purely imaginary, to get its conjugate, just you have to multiply that by minus sign. Right. So therefore, we get the result this way. Therefore, example you can write. Right? Example you can write, people, like this. Z equals 3i, then z bar equals minus 3i. And another one more, z equals minus 4i, then z bar is plus 4i. Understand? Okay? Right. We count that as a knot, people. That only as a knot. Lit. So this here x, y real numbers, and then z bar is this. Right. First one and second one, write down like that. Right. People, till you familiar this all theories, do again and again, right? This is a very easy one, very easy one. I emphasize this much because this lesson contains more theories. That theories are typical to this lesson. Okay. As long as you are familiar with this theories and fundamental results, you can work out questions. If you don't have that in your memory, you can't work out. You will find very easy convenience in the future when we do questions if you have these theories well. Okay, right. Take this. Right now, people. Right? Any question here, people? No questions, I think. No questions. So you can ask the question. Yeah. Right. No questions. Right. People, now we have some more important results. Now these results so far we learned relating to the conjugate. Relating to the conjugate. Okay. Now some results available relating to the modulus of a complex numbers. Right. Let's learn those things. Right on another subject. Some important results, or more important results, or another important results. Right, whatever this we have learned. Right. But people, those are these. Number one, Z bar is equal to mod Z squared. Number two, Z mod is equal to Z bar mod. Right. Number three, Z1, Z2 product modulus. Z1 mean people a complex number, Z2 is another complex number. First we multiply them together. First we multiply them together. Okay. You know, when you multiply two complex number, the result is another complex number, no? Right? We said that, we proved that at the very beginning of the lesson, right? We said when two complex numbers are Z1 and Z2, the sum is a complex number, difference is a complex number, product is a complex number, division is a complex number. We proved. Like that, here Z1 and Z2 are two complex numbers. We multiply them, then the result is another complex number. For that complex number, people, we can find the modulus. How did you define the modulus of a complex number? If the complex number is x plus iy, then can remember the definition of the modulus of z, square root of real part squared plus imaginary part squared. This is the way. Like that, people, after multiplying this Z1 and Z2, we can find its modulus. The result this says this is equal to finding moduli values of this Z1 and Z2 separately and multiplying them. See here, Z1 and Z2 product modulus. Right hand side taken what? For Z1 and Z2, the modular taken separately and multiplied together. Okay. Yeah, this way. And people, number 4 is this. We take Z1 divided by Z2, its modulus. First, we divide Z1 by Z2. Division of two complex numbers, people. Another complex number, no? Then for that complex number also we can find modulus. This result says what? Division of two complex numbers modulus is equal to, people, taking separately modulo of the numerator and denominator complex numbers and we divide them together. We take Z1 numerator complex number modulus, we take Z2 modulus, denominator complex number modulus. When you divide that two, it is equal to that division of two complex numbers modulus. These are very important results, right? Okay, the other one is, people, this number 5. Z1 plus Z2 modulus perfect squared plus z1 minus z2 modulus perfect squared I is equal to this way, people. This is the fifth result. Result number 5. Fifth result is this. Right? Yeah. Okay, people, let's see how to prove this one by one. These proofs are also very important proof. This one, this one, this one, this one, and this one, you can see, right? Very often in past papers. Very often in past papers. So therefore, this lesson is actually, this all we have to learn, people. After learning this theories, a very small question coming to the paper. We can very easily work out this. This advantage you will learn, people. You will realize this advantage of learning these complex numbers after entering the university, when you do the second year, third year, and thereafter till the end, especially when you do engineering courses or any course relating to electrical and electronics, you will find more application of these complex numbers. Okay, so for that situation, people, this is a good opportunity to get a good idea and a particular confidence about the lesson, and you have heard something about complex numbers, then you can give a good approach at that time, because these theories never you will learn these theories. This is the only location or position you learn these complex numbers basic theories, and after entering the exam, university people and the lecturers, they will start beyond this point will stop in the lesson. That occasion, these studies people huge back, right? And though we of course come in after you, teach to you, asking whether you completed notes, understood, did you work out the questions, how many past papers you did, that sort of questions you can hear at last in your lifetime at the A level. Thereafter, people at the university, nobody will inquire from you, did you understand? Really, you understood? And did you work out the questions? No, people. Then you have to learn self-studies, means that university. That occasion, only you will understand by at the A level, if you get particular pickup, right? Thinking something, once you are given some properties, now you can think using that properties and you get some results by thinking alone yourself. That ability, people, will be very helpful in learning at the university. But at the university, people, really, we don't say that we are going to learn more. There we will know there are lots of things to learn, but we learn there are very little. Okay, anyway, people, you will use them at the university, and when you do higher studies relating to engineering fields, right? We'll come to these people, proof one by one. This is, come to the proof number 1. Number 1 proof. Right, this way I take, let z equals x plus iy, right? Here x comma y are what real numbers, right? You know, people, the definition of modulus. Then you can write z bar going to be x minus iy, modulus of z going to be, people, real part perfect squared plus imaginary part perfect squared. This we know. Then I'm going to multiply, people, this z and z bar. This and this we multiply. X plus iy times x minus iy, right? Now this is a plus b into a minus b. That is nothing but a squared minus b squared is x squared. Here I squared is minus 1. That minus and this minus make plus y squared. Z bar. But people, this means it's nothing but the perfect squared of this. No, when you square this one, root will eliminate. We get the answer as x squared plus y squared. That is what here we have. Then that is nothing but mod z squared, right? This is the mod z squared. This is z bar. So therefore, people, this is the first result we prove. Right, people, this says us what? This says us, when we have a complex number z, its modulus perfect square can be obtained by multiplying that complex number with its conjugate. When we multiply complex number z by its conjugate z bar, the product will be, people, modulus of that complex number perfect squared, mod z squared. This is what the result. So therefore, whenever you see z bar, people, you can write for that product mod z squared. Right. And the other thing is, you can very clearly understand this mod z. For the mod z, you get positive real number, remember. Positive real number or 0. 0 comes when the complex number is 0. For the mod z, we get positive real number. Right? Okay. That is how we take the first result. Right. Number 2, people. You can write this mod z is this. Now z bar is this now, people. Then z bar mod. X squared plus. We know the modulus of a complex number is obtained real part squared plus imaginary part squared. Imaginary part squared. The imaginary part coming, people, here you can write this one as x plus I times minus 1. So now z bar x minus iy, you can write as x plus, taking I before and taking this minus in with this y minus y. So here, people, this is the real part and this is minus y is the imaginary part. Because the standard complex number takes the form x plus iy. Right? In between real and imaginary number, we should have a plus sign. Then I, then the imaginary part. So in that form, when I construct this, we get our imaginary part as, people, minus y. So then when you define the modulus of a complex number, it is square root of real part squared plus imaginary part squared. Right? So therefore here minus y squared. But you can very clearly see here minus y squared is, people, plus y squared. Then we get this here. X squared plus y squared. Yeah. Then you can see we got for mod z this mod of z bar this. You can see the right hand side being equal. Therefore, left hand side is equal. Therefore, mod z is equal to mod z bar. Right now, yeah. Right. People try to prove the number 3. I'll give you 2-3 minutes. Prove the number 3. Right. These two we can take very easily like this. Right. This is how we prove them, people. But your answer is correct. The way you got is correct. Yeah. Then people, now I'm going to prove the third and fourth like this. Yeah. People, now once I prove here this one, I'll use particular method. Right. So once I use that method and get this result, you might get the answer. Why I couldn't get this method to my mind. See, people, after learning that only, you can match your knowledge to get that answer that way. Then it says, just knowing the theory is not enough. We should know how to apply that. So therefore, people, in order to apply that theory, the theory permanently in a deep memory you should have in your mind. That is not enough, people. So you have practiced how to use them. See, now, once I use this method, you will get this feel into your mind. Right. Now you can very clearly see here, third one, this way. Z1, Z2. People, now you know Z1, Z2. Z1 is a complex number. Z2 is a complex number. Then their product is another complex number. Then I write here in this board. Yeah. Z dash, Z1, Z2 product. You know Z1 is a complex number, Z2 is a complex number. Their product is another complex number. I am going to take that as Z. Right. Then now I need the modulus of this, more people. Modulus of Z1, Z2 product. Since this is a complex number, its modulus only we need to find. In other words, I need this modulus of Z. This only I need. Right. Even I am going to write this Z1, Z2 modulus perfect squared I am writing. People, that means this no Z1, Z2 modulus perfect squared. But we said for the product of Z1, Z2 as Z, no, people. Really, mod Z squared only I am going to find there. People, mod Z squared, just now we wrote as, people, Z bar. Mod Z squared, we wrote as Z bar. Then, can you understand this Z1, Z2 product is a single complex number. There I have assumed that as Z. Then its modulus perfect squared I can write this complex number Z1, Z2 I have to multiply by its conjugate. Its conjugate. I think I am correct. That is because of when we consider here mod Z squared is equal to the complex number this multiplied by its conjugate. Using that, I can write now Z1 product is the complex number. Its modulus perfect squared will be equal to the complex number Z1 multiplied by its conjugate. Okay, right. Now, the previous one we proved when we have this way product, its conjugate, we said, people, we can write as conjugate of the first one multiplied by the conjugate of the second one. Previously we proved that, no? Z2 conjugate is equal to Z1 conjugate into Z2 conjugate, like that. So then I can apply it. that conjugate here for this Z1 and Z2 like this. Z1, Z2 times Z1 conjugate into Z2 conjugate. That is, of course, by the previous result. I think you can remember that Z1, Z2 conjugate we can write as Z1 conjugate, Z2 conjugate. This we proved. Okay. Now I can write here we have a product. With that we have product this. Then I can write people Z1 and Z1 bar. I can write Z1 into Z1 bar. I can write Z2 and Z2 bar. I can write like this. People, you can remember multiplication of two complex numbers is another complex number now. You can see Z1 and Z2 when two complex numbers, right? This product Z1 Z2 product is complex number. People, when you multiply this by another complex number Z3, this product is a complex number, that multiplied by this is another complex number. People, in this case, when you change the order, Z3, Z2, Z1, this way, still the product being equal. So therefore, people, here, Z1 is a complex number, Z2 is a complex number, Z1 bar is a complex number, Z2 bar is a complex number. Then four complex numbers we have to multiply. Therefore, we can multiply them in any order. Then I take the order to multiply this way. Z1 and Z1 bar I multiply, Z2 and Z2 bar I multiply. Then you can very clearly understand, people, Z1 into Z1 bar. It's like this, no? Z multiplied by Z bar. What is that? Mod Z squared. Like that, what is this? Z1 into Z1 bar. It is mod Z1 squared. Huh? Z1 modulus perfect squared. What is this? Z2 modulus perfect squared. So left hand side, people, we have this. Huh? Right. Now what we do, people? Now we take positive square root on both sides. Because we know modulus of a complex number, we get positive real number. Then we take positive square root. And this implies the required answer. This answer. See, people, here I use this method. Is there any objection? Is there any objection regarding this method? No, I think no. Then why couldn't you use this method? I did not use anything you don't know here, the things I used so far. Everything you know. Then why did you unable to use this? Because of people practice. We don't have such approach. Why? Because of less what? Experience by doing the questions. You know everything. This is 100% we agree to this method. And in proving them, the results are used also, you are familiar. But you get the idea, why couldn't we get this method when you work out this? People, how many of you use this method to get this answer? There may be some students. How many of you use this method? Are there? I think no. That is because of people, not your error, your fault. This is how the learning. This approach you get to your mind, people, once you do questions only. So therefore, just knowing the theories, people, you can't give the approach, good approach to get the answers. Most of our students, they think covering the whole syllabus and theories means they are okay. No, people, not at all. Not at all. So therefore, these approaches we have to remember one by one. By this way, people, collecting some methods only, we will be, of course, coming toward a particular good level so that we can work out the questions at the examination. Right. Right. Asking when we need to prove this one, should we use the previous one? No, this is accepted. The earlier one also correct. If you have more time and if you, of course, like to do like that, you can use this method. These people accepted at the paper, right? So now you can take this answer also in the same way, right? We'll prove that one in the same way, right? Number 4, fourth one. Z1 divided by Z2 modulus perfect square. You know, people, here Z1 divided by Z2, when you divide a complex number by another complex number, the result is complex number. No? Then really within this modulus sign, we have a complex number. Its modulus perfect squared, asking. But we know complex number is its modulus perfect squared is really that complex number into its conjugate. Then like that you can write here what, people? Z1 divided by Z2 is the complex number that multiplied by its conjugate. This way. Now in the early part, we noticed that, people, when we have this way a division, its conjugate can be written down as how people apply this conjugate for this numerator and denominator separately. Right. Right. This one we put. This one you can type this way. Okay. Now again, I can multiply, people, this. Z1 we multiply with its conjugate Z1 bar. Z2 we multiply with its conjugate Z2 bar. Yeah. So then see, you get this result. Then we get Z1 divided by Z2 modulus perfect squared is equal to Z1 into Z1 bar divided by Z2 into Z2 bar. This is nothing but, people, Z1 mod perfect squared, Z2 mod perfect squared. Then take in the positive square root, there you get this answer. Right? Okay. This is all we take. Right. The next one, people, now. Who got this next answer? This one, this result. Yeah. People, number 5, I'm going to take like this. Z1 plus Z2 modulus perfect square. This is the first one. I'm going to obtain an expression for this. Z1 plus Z2 modulus perfect square for this. People, you know, when we add two complex numbers, the result is another complex number. No? Then this is really a complex number. This is a complex number. Its modulus perfect squared. Its modulus perfect squared we have. Complex number modulus perfect squared. How to obtain? that complex number we should multiply with its conjugate. We prove that now, people. Mod z squared is equal to z conjugate, z bar. Then for this z only, here we have z1 plus z2. Why? We know sum of any two complex numbers is another complex number. So therefore, to obtain the modulus perfect squared of this complex number, people, I can take this complex number z1 plus z2, it is multiplied by its conjugate. Yes. I think you agree with me. Now, people, here z1 plus z2 conjugate, we proved I can apply this conjugate for this complex numbers separately, and this bracket I can write z1 plus z2 conjugate is equal to z1 conjugate plus z2 conjugate. That way you can write. Okay, so then I get this one like this, z1 plus z2, and what people z1 bar plus z2 bar, like this. You get. Now we have to remove the brackets. By this z1, we should multiply both this, and people by this z2, we have to multiply both this and take one expression. Keep that as number 1. Secondly, people take this in the same way, simplify and obtain the second result. Since we need the sum, add that two results together, then you get this answer. Right, hurry up, people. Right. Right, now what do you get there? Z1, Z1 bar, Z1, Z2 bar, Z2 is Z1 bar, Z2 is Z2 bar. Mod z squared here, mod z2 squared. People take this as number 1. Right. Similarly, take z1 minus z2 mod perfect square. This is really z1 minus z2 times z1 minus z2 conjugate. This here. Then this conjugate we can apply on this and this. Right. Now we multiply this and this. Z1 into Z1 bar and this minus Z1 into Z2 bar minus Z2 into Z1 bar plus Z2 into Z2 bar. This is people nothing but mod Z1 perfect square. Mod Z1 perfect square, this and this, right? And we'll keep like this. This is mod Z2 perfect square. You know the reason. When you multiply a complex number by its conjugate, what do you get? Its modulus perfect square. People, this is number 2. This is number 2. Now add this 1 and 2. Add this 1 and 2. Right? So then you can see this Z1, Z2 bar here minus Z1, Z2 bar will cancel off. Z2, Z1 bar will cancel with this minus Z2, Z1 bar. Then people, we get the answer. Right? Take 1 plus 2. Add this. You get what? 2 times. What is that? 1 squared plus what is that? 2 squared. This way we get that answer. Right. Right now, people. Right. These are the theories you should know how to prove. But some more proofs available in the lesson. But these are the fundamental things that you know and how to prove these. Right. Right. People, now the second one. Next important theory. Next important theory. Right. Here we learn again another one called as people Argand diagram. Argand diagram. Argand diagram, right? Is our next subheading. Write down next one as Argand diagram. Argand diagram. Right. People, another approach of another sect of the lesson is the Argand diagram. Now in the lesson, another story begins. To another sector we move by the Argand diagram. Right. People, this Argand diagram means the same plane containing 2 axes x and y. You know, the plane containing 2 axes x and y. That plane is called as the Cartesian coordinate plane. Cartesian coordinate plane. Right? The Cartesian coordinate plane means when we draw this way the 2 axes, this is a positive x-axis, negative x-axis, negative y-axis, positive y-axis. This is the origin of the 90. When we draw on a plane like this 2 axes, people, this is called as the Cartesian coordinate plane. Right. People, the same plane only we consider as the Argand diagram, or sometimes called as Argand plane. Argand plane. But there's a little amendments in it. This x-axis, people, we term as real axis. Y-axis we term as, people, imaginary axis. That's the only difference between the Cartesian plane and the Argand plane. This is now a real axis. Positive real axis is this. This is negative real axis. Negative real axis. This is called as, people, not y-axis, imaginary axis. Okay, this is negative imaginary axis. Negative imaginary axis. Okay, people, then what are the numbers available on the axis? On this axis, what are the numbers available? The usual numbers. What? Here 1, 2, 3, 4, 5, and so on. Here negative values. -1, -2, -3, -4. And here also, people, 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. Okay, the same real numbers available. Then this plane is called as, people, Argand plane or Argand diagram. This is called as the Argand plane or Argand diagram. Actually, this part of this complex number is, of course, found or introduced by one mathematician called, well, famous mathematician Argand. Right. So for his name, this is term now, Argand plane. All right, people. Now let's see what use we have with this Argand plane. Okay. Well, you can very clearly understand. In Cartesian coordinate plane, only the same plane, but the axis different. X and y axis come in that case. When you consider Cartesian coordinate plane, x-axis, y-axis, origin. People, when we consider point P, coordinates 2, 3. Okay, that 2, 3 coordinates being, people, 2 mean the x coordinate. No, the distance along x-axis is this first one. 3 mean the distance along y-axis. This way. Right. Now, people, here if I consider that point P 2, 3, for example. P, 2, P 2, 3. Then what is, people, 2? What is 2? Is it x coordinate? No. We don't use the word x, because we use the word x when this axis is x-axis. Now this axis is real axis. Then this 2 is a real part of what? Of the complex number. What is this 3? Not the y coordinate. Now this axis is imaginary axis. Then this is called as the imaginary part. Then, people, this is our tracing or the correspondence. Now, this way when we consider Argand plane, by a point we get 2 coordinates. All right, people? Hereinafter we don't use the word coordinate also. We get 2 parts, not the word coordinate we use, 2 parts. By a point we get 2 parts. First part is the real part, that is coming along real axis, the length. Other part is the imaginary part of what? Of a complex number. It is coming along the imaginary axis. Therefore, people, in this case, we define by a point on the Argand plane, we get the real part and imaginary part of a complex number. Understand? People, you know, when we have, or if we have real part and imaginary part of a complex number, can we write the complex number? Yes, possible. Then corresponding to that point P, the complex number represented at the point P, if I denote by ZP complex number is people 2 plus 3i. Then remember, in this case, we come to another new world, but now we can represent a complex number by a point where in the Argand plane, not the Cartesian plane. We don't use that one. In the Argand plane. In the Argand plane, by a point, we can represent what? A complex number. We can represent people, right? Do we really get the complex number? No, not as it is. Then what do we get by the point? By the point, we get the real part and imaginary part. If you know the real part and imaginary part, we can write the complex number this way. So then the point gives us the real part and imaginary part, which we should have to write the complex number. If we have those real and imaginary parts, we can write the complex number this way. So therefore, people, every point in the Argand plane now, having that real part and imaginary part, for each point, taking the real and imaginary part, we can write a complex number. Then you can see in the Argand plane, how many complex numbers available? Infinity. Why? Every point has a complex number. Therefore, we say that this is known as sometimes people complex plane, Argand diagram, Argand plane, and complex plane. Another word we use, complex plane. Complex plane means people, the plane containing complex numbers. The plane containing complex numbers. Understand? This Argand plane, therefore, containing, right, infinitely many points. Each point can represent. Each point, people directly never gives what? Never give a complex number. But the point gives us real part and imaginary part. If we know the real part and imaginary part, we know how to write the complex number. That is how we say every point represent a complex number. So therefore, corresponding to any point on this plane, people, there is a what? Complex number. Then this Argand plane dense of what? Complex numbers. So therefore, this plane is called as sometimes complex plane. Okay. Then for example, people, this point P, usually we don't write 2, 3. Some occasions for our convenience we write. Then how do we write the point P? Point P, people, we must write this way, 2 plus 3i. Right? Usually we no longer write this way, coordinate form, 2 plus 3i. What's the reason, people? We said every point gives on the Argand plane a complex number. But people, we write sometimes we write the coordinates form, real part and imaginary part, not coordinate, real part and imaginary part, as I have written earlier here, 2, 3. When we need some occasions the parts form, real part and imaginary part, this way we write. But people, the usual practice is writing at the point the corresponding complex number, writing in the form x plus iy. Okay. All right. Now, people, you have to understand this thing very carefully. We can represent a complex number in the Argand plane by a point. By a point. Thoroughly get this idea, because using the same Argand plane, we are going to express the complex number in the next case as geometric form. People, these are the things you have to take thoroughly, severely, strongly to your mind in order to link one to other. Understand? If you can do that mentally, people, you will win the game. Therefore, the representation of a complex number now we can do by a point on the Argand plane, not on the Cartesian plane, right? We have Argand plane. Right. Now then, people, we know this point is 3, no? Actually, when we write people, this coordinate of this point, coordinate means I use that one for our convenience of thinking, 0, 3, no? 0, 3. Then, people there, the corresponding complex number, if I write, real part is 0, imaginary part is 3, therefore 3i. The corresponding complex number is 3i. 0 plus 3i mean people, really 3i. Then somebody might ask, sir, we usually mark on the y-axis only this 3. But this is not y-axis, right? This is imaginary axis. At every point on the complex plane, it represents a complex number. Then this point gives us the complex number 3i. Then if we mark this point as 3i, is it wrong? No, that's correct. That's correct. Then furthermore, you might ask, so then is this point 3 or 3i? Sometimes you might ask the question, is this point 3 or 3i? People, 3 or 3i, we never get confused. This point is 0, 3 point. Real part 0, imaginary part 3. Right? This point shows real part 0, imaginary part 3. Then once we write the corresponding complex number, it is 3i. Therefore, people, though you mark here 3i or 3, both are correct. But since they are correct, people, usually when you mark this way, the way we mark the numbers on the y-axis, we can mark without marking this way 3i or without I. Then you can very clearly see, people, the reason why this axis is called as imaginary axis. Why? When we consider any point on this imaginary axis, the real part is 0. It has only the imaginary part. Taking that imaginary part, when you write the complex number will be of the form a real number into I. Product of real number and I, we know, people, the resulting number is what? Imaginary number. So therefore, on this axis, everywhere on the axis, when we consider a point, that point gives us imaginary number. That's the reason, people, this is called as imaginary axis. Okay, then on this vertical axis, people, all the numbers we have are what? Imaginary numbers. Imaginary numbers. Understand? Imaginary numbers. By a point only, complex number is represented. That point, people, we identify giving an imaginary number. Okay? Right. So this is the introduction for the Argand diagram. So therefore, by any point on the Argand diagram, we can represent a complex number. Then on the imaginary axis, we have all complex numbers are imaginary numbers. On the real axis, when we consider, people, any point like this is 2, 0, this point. Then the corresponding complex number, we can write 2 plus 0i. Then it is 2. Then we can very clearly understand any point on the real axis represents purely real complex number. Understand? Purely real complex number. So that means all numbers by the points on the real axis representing real numbers. That complex number is a real now, purely real. So that is why this is known as, people, real axis. So therefore, you can mark on this imaginary axis 1i, 2i, 3i, and so on. Okay? Or else, people, the coordinate form 1, 2, 3, and so on. Because before writing the complex number at that point, we have written down what? Real part and imaginary part of that point. Real part means the distance along the real axis. Imaginary part means the distance along the imaginary axis to that point. That only we write first. So therefore, that is always okay. Thereafter, only using that real part and imaginary part, we see we can write the complex number. So therefore, we correspond that point, we attach to that point the complex number. So therefore, on the imaginary axis, if you mark 1, 2, 3, and so on, no, 1i, 2i, 3i, so on, both are correct. Okay, both are correct. Right. Now, this is what people we have to learn next. Argand diagram is the heading. We'll write the Argand diagram people. Heading. Write down Argand diagram. Argand diagram is the heading. Now write a brief note. Consider the plane, the Cartesian coordinate plane, the Cartesian coordinate plane. Consider the Cartesian coordinate plane containing the two axes capital X and capital Y. Right, now write and start from the line. Let us take the x-axis as real axis and the y-axis as imaginary axis. Imaginary axis. Imaginary axis. Then the plane is known as Argand diagram. Argand diagram. Or within bracket write down Argand plane. Argand diagram within bracket O Argand plane. Start from new line. When we consider a point on the plane, when we consider a point on the plane, it has two coordinates. It has two coordinates. They are now real part and imaginary part. They are now real part and imaginary part of a complex number. Of a complex number. Of a complex number. Therefore, using this real and imaginary parts, we can write the corresponding complex number in the form x plus iy. Right on here, x is the real part and y is the imaginary part. Y is the imaginary part of the point. Y is the imaginary part of the point. Write down. In this way, for every point on the Argand plane, there is a unique complex number. There is a unique complex number. There's a unique UNIQUE, unique complex number. Unique complex number. Write down. Therefore, the Argand plane contains infinitely many complex numbers. Infinitely many complex numbers and therefore it is sometimes known as complex plane. Complex plane. Right, people, draw this diagram. Draw this diagram. Right. Draw this diagram. Mark this point P there, 2, 3. No? No, yeah, now you can write, people. You can write point P gives real part 2 and imaginary part 3 and imaginary part 3 of the complex number. Therefore, point P represents the complex number two plus 3i. Two plus 3i. Right. Now, people, you should have the idea. When we consider this Argand plane, at every point there is a complex number. Okay. Right. Now, people, suppose like this. I'm going to take another point, this one, say Q. Real part 5, imaginary part 1. Right. Point P is this. People, now I am going to join this P and Q. I'm going to join these points P and Q. Right. On the point Q, I am going to take people another point as R. This R divides this line PQ in the ratio, suppose 2:1. Suppose 2:1. Okay. Now, people, this point R also another point on the complex plane. Therefore, that should represent a complex number. People, to write that complex number, we should be able to find the real part and imaginary part of point R. If I take that as x bar y bar, real part and imaginary part as x bar y bar. People, really, though we don't use the word coordinates, if we people ignore the real axis, imaginary axis, this is nothing but what? Cartesian coordinate plane. Then for a while, we ignore this real and imaginary axis. Then we have what? Cartesian coordinate plane. Then x bar y bar are what? X and y coordinates of the point R. Then you can suggest me a method of finding this x bar y bar. What, people? The ratio theorem we learned in coordinate geometry. Using ratio theorem, people, you can find this x bar y bar. Right? If I take this complex number represented by P as ZP, that at Q as ZQ, both this ZP and ZQ you can write. Both this ZP and ZQ you can write. ZP stands for, people, complex number represented by the point P. Then ZP is nothing but 2 plus 3i. ZQ 5 plus 1 times I. Now, using the knowledge of the coordinate geometry, the ratio theorem knowledge, people, now I can write the point R, x bar. What are that, people? 2 times 5, 1 times 2, divided by 2 plus 1. Y bar 2 times 1, 1 times 3, divided by what? 2 plus 1. Then I can write, people, the corresponding complex number represented by R. Is it that? X bar plus IY bar. X bar is this 2 into 5 plus 1 into 2, 2 plus 1. Plus I times Y bar is 2 plus 1. Now you can write Z dark. This 3 I take as a common denominator. Right. People, here this 2 and here this 2 I take out. So what do you get here? 5 plus there I. And here 1 and here 1 I take out. 2 plus 3i. 5 plus I is nothing but Z cube. This is Z cube. 2 times Z cube. This is 1 times 2 plus 3i ZP. 2 plus 1. See people, what is this result? The complex number given by R can be directly found, people, the same ratio theorem which we used in the coordinate geometry lesson. It's a dark, this complex number. Now we've written how, people? 2 times ZQ here. This ratio times other side complex number, 2 times ZQ plus 1 times ZP divided by 2 plus 1. The same way we can apply the ratio theorem in the complex plane too. That is because of, people, the same meaning. The same meaning. So therefore, whenever we find a complex number with the help of another 2 complex number which lie on the same line, people, we can use a ratio theorem. So therefore, this is another approach. Understand? The ratio theorem you can apply. Okay. Let's see. 1 by 1 we can join. We can join 1 by 1. So people, this kind of thing we can join if we have the previous knowledge well. If you don't know what is the ratio theorem, when I try to explain as much as possible, people, nobody will realize. So then the student might say, no, it's confusing, we can't understand. People then go where? Somewhere else without doing maths. Okay. So we should have what, people? A good rhythm. So everything is joined to the previous one. It's like a chain. So that is why I said at the beginning, go through all the notes and be ready for the next lesson. So now, people, when we can see that link this with the coordinate geometry, people, then only deeply we can keep this thing in our memory. Then only we accept that. Then only, people, we can think. Because all the weapons now with us we have. With the weapon, people, now we can fight. If the weapons are not sharpened enough and some weapons are lost, those people think this is full of theories. We can't understand, people. That way, of course, nobody can do this one. This is like a story, people, like a story. A story, if you miss a certain part, people, the story discontinues. Then those guys, they can't understand. Then the people, they come here and there to the classes, no notes and so on. Those guys, of course, people, this rhythm they won't get. Therefore, they can't work out this question at the paper. Okay, this is like a slide meditation. Okay, right. Okay, now we go to the next one. Ratio theorem for the what? Complex numbers. Ratio theorem for the complex numbers. Right. Write down. Ratio theorem. Ratio theorem. Right. Try to like these people. Ratio theorem. Write down, let the points P1 and P2, let the point P1 and P2 represent the complex numbers, Z1 equals x1 plus iy1 and Z2 equals x2 plus iy2 complex numbers Z1 equals x1 plus iy1 and Z2 x2 plus iy2 respectively, where x1, x2, y1, y2 are real numbers. Right, like this. Suppose point capital R, divides the line P1, P2, divides the line P1, P2. People write down divides internally. Divides internally. The line P1, P2 in the ratio P1R divided by P2R equals mu by lambda. Then the complex number represented by the point R is lambda times Z1 plus mu times Z2 divided by lambda plus mu. Divided by lambda plus mu. Right, people? Now we come to the proof of that. Right? Come to proof of that. I take this as real axis. This way I write that. This is the imaginary axis. I write it like this. Suppose people here we have point P1, right? Complex number represented by this is Z1. The coordinates going to be people, right? If we use the word coordinates, that is wrong to use, but people never mind. Right? That I we use imaginary unit as I know, but actually it's iota no people. Right? The word familiar we can't remove easily. Coordinate means really real part and imaginary part, right? Remember like that. Okay, right. Here I use the word coordinates because coordinate geometry knowledge I am going to use here. The point P1 is x1, y1. Point P2 here, people, representing the complex number Z2 in coordinates form x2, y2. Then P1, P2 we join. And this is R. Let it be x bar, y bar. P1R is mu, people. P2R is lambda. Okay, draw this diagram. This is the origin. Negative imaginary axis, negative real axis. Draw the diagram, people. Right. Now you can write by coordinate geometry. By coordinate geometry. After proving, you can write by coordinate geometry. X bar equals what, people? Lambda times x1 mu times x2 divided by lambda plus mu. Y bar lambda times y1 mu times y2 divided by lambda plus mu. Now you can write the complex number represented by the point capital R. The complex number represented by point capital R is x bar plus iy bar. X bar plus iy bar. Okay. Then substitute for this x bar and iy bar. X bar is what, people? This, no? Lambda x1 plus mu x2 divided by lambda plus mu y bar. Like this. Okay. Now you can write people next. Right. Here we can take lambda out, lambda plus mu we can write at the denominator. So take lambda out, x1 plus iy1 mu times 2 plus iy2. These people is Z1. This is Z2. Lambda plus. This is a complex number represented by people point R. All right. So then people understand first thing what? Whenever we use Argand diagram, the coordinate geometry knowledge we use. Understand? Right. By the other theory, people, you will realize the complex number have people vector properties, vectors. In theories of vectors also we can apply. And that is the place where this complex number people play in a huge role where in electronics and electrical. You know, when current is moving along a particular direction, people, magnetic field forming. I can't remember the left law and right law now. I can remember like this, no? Current is this way, magnetic field this way. That direction can be given by these complex numbers. Okay, that is the place. The complex number, people, when we introduce for the complex number, the geometrical presentation, we give that next. There you will realize what the complex numbers will have the all properties of vectors. See here then, when somebody work out the questions in complex numbers, the coordinate geometry knowledge, vector knowledge, both he must have. Otherwise, he can't understand this. We are really using people the elementary properties of that two lessons for this, but we will learn furthermore by the another law we learn here that is available in the new syllabus, in your syllabus, right? By that law, people, you come to another what side of the lesson. That side only we develop for our higher studies application in maths, right? Now, then people, if this R becomes midpoint, mu, lambda both being equal, then ratio going to be 1:1. Then the midpoint complex number can easily be found. Put in for lambda and mu each one. Then write down like this as a note. Write down as a note. Let capital R be let capital R be the midpoint of the line P1 and P2, of the line P1, P2. Let capital R be the midpoint of the line P1, P2. Then lambda equals mu equals 1. Lambda equals mu equals 1. Then the complex number represented by the point capital R is what? Z1 plus Z2 divided by 2. Put lambda 1, Z1 plus mu 1, Z2 divided by 1 plus 1, 2. Midpoint complex number is that. Right. Right. So then we come to the break. The 2 hours, if we can manage the class, that's fine, without disturbing us by this electricity, right? Okay. We will come to the break and we'll start the class after, yeah, at 10:25, we'll start the class, right? 20 minutes break enough. Right. Right, people. Then we'll continue lesson here. Okay. Next thing. We know this ratio theorem now for complex numbers, right? Okay. Next thing is, people, how to mark the sum and difference of a complex number. We have to learn here, right? Now, first of all, I'm going to use this Argand plane to show how can we mark negative complex number. Negative complex number of a complex number. Right. Now, people, suppose for example, I'm going to take a complex number as this, say z equals 3 plus 4y. Z equals 3 plus 4y. This complex number, people, is represented by the point. If I talk about the coordinate form, the point which has the coordinates 3, 4. I use the word coordinate here for our convenience of thinking, because coordinates only, people, we get at once when we mark like this rather than the real part and imaginary part. Okay. If you take, people, this point as P, by the point P only, we get this complex number, right? Okay. We get this complex number. Right now, here, this is 3 units. This is 4 units. Right. Then the people, this is the point P representing the complex number Z. Right. Now, we come to the form, people, the next one, this. When I join this O and P, OP line, this is 4 units now. This OP line, we can write its length. OP squared is therefore 3 squared plus 4 squared. Now OP we can write 9 plus 16 root OP is 5. OP is 5. Right. Now, people, if I find the mod of Z, what do you get? 3 squared plus 4 squared root. That's also 5. All right. Now, people, you have another meaning. Now we are going to give the geometrical meaning for the complex number. Then you can very clearly understand modulus of a complex number mean what, people, really. Modulus of a complex number mean what here? The distance from the origin to the point which represent the complex number in the Argand plane. Understand? Okay. The distance from the origin to the point on the Argand diagram which represent the complex number. That is a modulus. This OP length is, people, modulus of Z. Understand? Right. Well, now I'll take this. Z equals 3 plus 4y. Right. Now I'm going to take this angle, the OP line segment, make it with the positive real axis in anticlockwise. This way. The OP line segment, people, makes an angle theta with the positive real axis in anticlockwise. Right. Now, people, you can write this tree. Using this length, OP cos theta. This 4. You can write OP sin theta. 3 is OP cos theta, 4 is OP sin theta. Then I take this. For this 3, I put OP cos theta. For this 4, I write OP sin theta. I can take this OP out. Cos theta plus I sin theta. People, what is OP? OP is 5. That is mod Z. People, this OP, I write as mod Z. Right. Now see, people, that complex number, this we could write. Here we have mod Z, that is really 5. Huh? This is right, really 5. What does this 5 mean, people? Length of this line segment multiplied by here cos theta plus I sin theta. What is this theta, people? This angle we said. What angle? The OP line segment makes with the positive real axis anticlockwise. That angle available in the bracket. People, now, can you remember the same complex number, this we have written down on the right hand side using 2 properties of a line segment. What are the 2 properties, people, available on the right hand side? Length of the line segment OP is here. Okay. And this angle theta used here. People, angle theta, when you change this angle theta, increase or decrease, you can see this OP line segment, its directed direction is changing. In this case, the directed direction I take going away from the origin like this. Now that direction of this arrowhead changes, people, once you change this theta. People, now you get a nice idea. But in writing the right hand side of this complex number, we have used 2 properties of a line segment. What is that, people? Length of the line segment that we have used here. Its direction is given by theta now, people. Once you change that theta, direction obviously change. You can very easily see that by the diagram. That theta here we have. People, then the right hand side contains the 2 properties of a line segment. What? Magnitude and direction. The length of the line segment and its direction. Now you can very clearly understand. The right hand side contains the property of a vector. Why? If we can explain something by using the length of a line segment and its direction, then that quantity should be a vector. Therefore, the complex number has, people, the nature of vector. Then, people, we can represent the complex number in another form. What is the other form? The other form is, people, by using a line segment. In this case, the OP line segment. What are the things we need of the line segment to represent that corresponding complex number? The length of the line segment we need to place here. And once we draw the arrowhead going away from the origin, that line segment, the angle it makes with the positive real axis in anticlockwise. That angle we need to place here. Then you can obviously see the 2 properties we take, the length of the line segment and its direction. That 2 properties available on the right hand side. So therefore, the right hand side has the vector quality. Therefore, the complex number now we can represent by using the properties of a line segment, its length and the direction. Therefore, now the complex number gets acquires what? The vector nature. Understand? So in this way, people, when you represent a complex number using the length of the line segment and its direction, that is called as the polar form. Polar form of the complex number. Polar form. Polar form means, people, using the length of a line segment and its direction. Using that two qualities, properties, we can express the complex number. Understand? Now, people, earlier we said what complex number has the coordinate geometry nature. Once we consider complex number is represented by a point on the Argand plane, then really we can use all the theorems which are true for the straight lines. Even for circles, we learn them future in the lesson. And now, people, using the property of the two properties of a line segment, now we notice we can express the complex number. Because of that, people, the complex number has what? Vector properties. Okay. People, this Argand, this angle is defined as the argument of the complex number Z. This point P represents the complex number Z, no? So therefore, this theta is called as the argument. Argument of Z, and it is simply written as this way: arg Z theta. Right? When we measure this theta, starting from real axis in anticlockwise, there we define the argument is positive. Some occasions we measure this angle. For example, suppose the line segment is in the fourth quadrant. Then if we use this way the angle to measure this direction clockwise, then we say, people, this argument is negative argument. Understand, people? So this is the approach for the vector form of the complex number. Right? Then, people, will come to that. Thereafter, we can go to mark the sum and difference of a complex number. Okay? Right. Right, people. Now we can write the next subheading like this: polar form. Polar form of the complex number. Polar form. Polar form of the complex number. People, this polar form, this polar form we had where in the straight lines also in our days. Straight line and coordinate geometry, you know. In our days, people, when we were doing A levels, that means long before, right? Long before. We had 5 lessons in coordinate geometry. Straight line, circles, parabola, hyperbola, ellipse. Right? Wait for a while. Those days for coordinate geometry, we had straight lines, circles, parabola, hyperbola, ellipse. And in addition to that, in the same lessons, we had, people, another one, polar form of a straight line. And polar form of a circle, polar form of a parabola, polar form of a hyperbola, polar form of a other one, ellipse. Understand? Then from one lesson, people, one lesson in the sense one part, first part is coming under Cartesian coordinate question, second part come in polar form. Then only 5 questions come in only from coordinate geometry. There, in each question, there are 2 parts. One is from Cartesian form, other one is from polar form. Now, completely the polar form removed from the coordinate geometry, and now you have only 2 lessons, straight lines and circles. And fortunately, this polar form available in the complex numbers at the moment. So if you won't get these two people, you don't know anything about polar form. But these polar form people, very important. Very important. In people giving the equation of motion of a object or particle in the space, right? In the space. I'll just explain that one, people. Now, suppose in a sphere, I have drawn that on the circle, on the board, that is two dimension. People, now suppose when we write, for example, projectile motion on the plane, right, like this, you get this equation only in terms of x, y, no, people. Now suppose while the particle is moving in the space, that particle comes out from the board and moving like this. Then once it comes out, people, the displacement out from the board we take as z. Then having only the relationship between x and y, you can't explain what the motion of the particle. Understand? Okay. Then in this case, we can, using the vectors, we can take another one as z. So then the position vector you can give, right? You know this one already. I just explained this way. Position vector of the point we can give, we can express like this. In the meantime, using the polar form, we can give this polar form. Motion in the three-dimensional space. Polar form, we can very easily explain this, right? So you will learn this polar form approaches when you learn in the university first year applied maths. Applied maths, nice applications available in polar form. By that, of course, we can very easily explain the motion of the planetary motion. Can be explained. You know, people, now when a planet is moving in the space, subject to a particular rule, no? That equation can easily be obtained this polar form. Understand? So nice applications available. Most of the students, this is called as a classical mechanics in the applied maths in the university. Just if you have brothers and sisters, how was the classical mechanics in applied maths? Everybody, I think, will give you a very bad answer, very difficult to think. Because people, this approach is for the three-dimensional space. Bit inconvenience to take idea. If you don't concentrate your mind there, then the variation cannot be understood easily once this thing happens where they are in the space. Okay. Now, people, in the previous syllabus, in our syllabus, we had what? Coordinate geometry. That not coordinate geometry, two-dimensional geometry and space geometry. Okay. So now at the very beginning, we had that lessons in order to give that particular environment in our mind to think about these situations once this something is moving in the space. Right? Space geometry. That lesson also removed now. Now, for example, people, can you imagine the point of intersection of two diagonals of a parallel pipe? Parallel pipe. Parallel pipe is something like this. Diagonals means, people, when you join this point and this lower point and this point and this lower point, they intersect at a point. Okay. So now just imagine. So people, these are really very important ones in maths. This is when we have parallel pipe. I just say this one for you to think a little bit about these things. In maths, this kind of things also available, people. Right? So this way, when we join it, right? is one diagonal, the other diagonal is this. Now, if I draw like this, people, I don't think that you can see this one. Anyway, people, just try to think this one. This kind of things, of course, are available. These two diagonals, they meet at a point. Like that. In the 3D geometry we had. People, if we have something like that, then that motion of a space using the polar form we can very easily discuss. Right? But still, the classical mechanics part in applied maths available in the university. Actually, I did this all because I did major subjects as pure and applied. Then very easily, of course, we can work out a question. Right, now I want you to tell you what people, the polar form is another good application in complex numbers, but in this case, the polar form we apply in the 2D plane, two-dimensional plane. Right? Okay. Then polar form, we can explain people. Polar form of a complex number. Now, I'll take like this. Write down like this. Let Z equals x plus iy, x comma y, real numbers. Write down. Be a complex number. Be a complex number. On the Argand plane, represented by the point P. Represented by the point P. Represented by the point P. Right? Right, people, now we'll draw a small diagram. Is the real axis, is the imaginary axis. This is the origin, no. Point P is this, that is represented in the complex number Z. This way, we mark this. Right. First come this. Right. Now we can come to next part. People will draw this way a perpendicular. This is x, no? This is y. Right. Now you can write people. OP length. OP length. Suppose R. I take it as R, people. OP length I am going to take as R. Right? It is, by the Pythagoras theorem, you can write root of x square plus y square. But mod Z is equal to people square root of x square plus y square. Therefore, mod Z is equal to OP. Therefore, we get geometrical meaning for what? Modulus of a complex number. Geometrical meaning for modulus of a complex number. right? That is nothing but the distance from origin to the point P. What is point P? The point on the Argand plane which represents the complex number, right? Now, people, if I put this way the arrow out means going out from the origin. Now this angle theta, we can explain. Before that, we'll come to this right now. One sentence. Therefore, the modulus of a complex number, is the distance from to the point P, is the distance to the point P from O. From O. From O. From O. Right. Next one, we write, people. Write down. Suppose the line segment OP. Suppose the line segment OP. Suppose line segment OP makes an angle. Makes an angle theta makes an angle theta with the positive real axis in anticlockwise sense. In anticlockwise sense. This angle is called as the argument of the complex number is Z. And it is written as arg Z. And it is written as arg Z. Write down this way. When this angle is measured in anticlockwise, it is the positive argument of the complex number Z. When this angle is measured clockwise sense, the argument is negative. right? The argument is negative. Right, now you can write people like this. Head on by the diagram. By diagram, you can write x equals r cos theta, y equals r sin theta. Therefore, z equals x plus y iy. We can write x is r cos theta plus I times y is r sin theta. Takes r out. Cos theta plus I sin theta. Cos theta plus I sin theta. What is this r, people? Mod of z. What is this theta here? And this arc of z. Now you can see this one and this. Those two variations, people, really the properties, the two properties belongs to a straight line. Straight line, people, when we consider vector, we always actually, we depend on what, people? We depend on the length of the line and its direction. That two only, people, here also we have. So therefore, this r, the length, belongs to this OP line segment. When you put arrow going away from the origin, the angle theta also belongs to what? This OP line segment. Then on the right hand side, people, we have used the two qualities of a line segment, length and the direction. That is why the right hand side we say, people, it has the vector nature, vector property. Furthermore, you can very clearly understand, people, this way. Suppose this line segment OP, I move away from here without changing its length and this direction. That means I bring this line segment from this position to another position so that the length OP does not change and the direction theta does not change. Now, suppose here we have that line OP now. People, now see the arrowhead also available there. See here, the two properties we said earlier, this R. Has this been changed? No, the same length. Has this angle theta changed? No. This doesn't change. R doesn't change. Still, R and this theta have the same value. Then, after bringing that line segment from there to another place, if we rewrite substituting for new values of R and theta, people, the same thing coming. Understand? Now, people, this line segment and this line segment have the same R and theta. That is another witness for what, people? By line segment, now we can represent a complex number. By a line segment, now we can represent a complex number. That is the next point, people. We can very easily suggest this complex numbers has vector form. You can remember, people, in the vectors we learned, when we represent by this pen a vector, this pen, of course, I bring parallel to itself to another location, to another location, to another location, to another location, and so on. We said, but people, the two qualities of a vector, the magnitude and direction, do not change by but moving this pen in the space here and there. Therefore, by every location, the represented vector by this pen people being equal. Similar thing here become property because become true people, because the two properties, once we replace this line segment OP parallel to itself without changing its direction, people, the both qualities R and theta still the same. So therefore, now we can give a complex number can be represented by a line segment. Earlier we said what? Complex number can be shown by a point in the Argand plane. Now we put more step, another one step more, and now we can say complex number can be represented by a line segment. What are the properties of the line segment we use here to represent the complex number? Its length and its direction. That is why we say complex numbers has the vector qualities. The vector qualities. Okay, people? Right. Okay. We wrote up to here. Right. Now we'll write, people, another one sentence like this. Write down. In writing the complex number, in the polar form, the two qualities of a line segment, the length and the direction have been used. Therefore, a complex number can be represented by a line segment using its two properties, magnitude and direction. This suggests the polar form of a complex number has vector property. Okay. But people, in the same diagram, we'll draw. We have to draw a line segment parallel to this OP from another location so that the same length available, right? This way. Same length available, right? This way. Suppose this is XY. Now write down, people, starting from new line. Suppose the line segment OP, has been shifted parallel to itself to a new position shown as in the diagram. Now, the line segment XY at the new position represents the same complex number Z as before. The same complex number Z as before. Right. Right, people? Okay, no? Right. Now, the XY line segment gives us the complex number Z. Right. Because of this, you can very easily accept that. People, now you can see the point Y and the point X are 2 points on the Argand plane. Then people, point Y represents a complex number. Don't mark this one. Now only XY you have to mark. Suppose the point Y represents the complex number Z1. Point X represents the complex number Z2, suppose. Because point X is a point on the Argand plane. So therefore, that should represent a complex number. We said but earlier, by any point on the Argand plane, representing a complex number, no? Right. So then, these 2 points, X and Y, represent the complex numbers Z2 and Z1. Right. And by the line segment from X to Y, we said it is representing the complex number Z. People, we can prove. I am for next. We can prove the complex number represented by the line segment OP is Z. The same complex number is represented by this XY. We agreed that. Now what I am trying to tell you is, people, that complex number represented by the line segment OP, and now it is by XY, the complex number is Z. That Z we can write, people, complex number at Y minus complex number at Z. That way we can write. This is to say, people, when we consider the position vector, if we have point A here, point B here, origin is here, null vector is the position vector. Suppose the position vector of A as simple A, that of B as people simple B. People, can you remember we wrote this AB vector? AB vector is equal to position vector of the second letter B minus position vector of first letter A. The same property become true, people, in this case. That is because of what? Because of that vector quality the complex number has. We can prove that one. Next one, I am going to prove that. Okay. Right now? Yeah. Right. Now, don't mark that Z1, Z2 at this X and Y. I will come to that later. Right. Now, people, here, in addition to this, we must understand another definition here. That definition is really the principal argument. The principal argument. Right, people? The principal argument. Right. You know, this argument of a complex number has 2 signs, plus sign and minus sign. Plus sign and minus sign. Okay. We know when the argument is measured, right, in this way, anticlockwise, this is a positive argument. Right. In this anticlockwise sense, people, we measure the angle this way up to this 180. Starting from 0 up to this 180, that range of the angle is called as the principal angle in the positive sense. In the positive sense, right? Then what is that? Theta less than or equal to pi, greater than or equal to 0. This range is called as the principal angle of the argument in the positive sense, right? Now people, when this argument is measured in clockwise, right, this way, then you know this negative, no? Then while we are measuring this way, the argument, when you come to this way, up to the negative x-axis, people, that range of the argument is called as principal argument in the negative sense. Then people, what is the interval here we can write? Theta argument less than 0 because it is negative, no? But greater than pi, minus pi, not pi, greater than minus pi. When we rotate this way, minus pi, no? So therefore, people, from the anticlockwise up to pi, the range of the angle is the positive and principal range in the positive sense. In the clockwise sense, from 0 to minus 180 range, people called as what? Principal part in the negative sense. Understand? Usually, at the examination, some questions asking people to express given complex number in polar form, including the angle, that means argument, in the principal range. Therefore, definitely, we have to put to a polar form with the argument. When you go from positive sense, that angle should be between 0 and 180, including both. If you can't give like that, people, that means when the corresponding line segment is in the third quadrant, people, you can't move this way. Why? Then you have exceeded the principal range in the positive sense. If we need to keep that answer in the principal part, then no longer exceeding 180 you can go, because our definition of the principal part in the positive sense ends at 180. Then you have to go this way. Then your argument is now negative. Okay, so therefore, people, we should understand here the principal argument. And if the argument of a complex number is in the principal range, in positive sense 0 to 180, negative sense 0 to minus 180. If the argument lies in that principal range, then to write such argument, people, we use the capital A, R, G, Z. Usually this capital A we use to denote principal argument. But people, if you don't worry about the principal argument, and if we use any argument, right, people, we use what? Simple A, arg, Z. Simple A we use, people, to say the argument is any. It can be in the principal range or out of the principal range. Understand? Right. We come to the next subheading, write down principal argument, write down principal argument as the next heading. Principal argument. Principal argument. Right, write down positive sense. Positive sense. In the positive sense, people, principal argument is real part, imaginary part, negative real part, negative imaginary part. This is the principal argument. Theta less than pi, greater than or equal to 0. Negative sense. Like this. real part, real axis, imaginary axis, negative real axis, negative imaginary axis. Theta people is then 0 but greater than minus pi. Right. This way we can write it. Right. This is positive sense, right? This is negative. Right. Write down. I'm drawing this a sentence like this, people. Write down. If the argument of a complex number is z, if the argument of the complex number is z lies in the principal range then it is written as argz. We use the capital letter. Then it is written as argz. And any argument, to write any argument, we use simple arg. Okay. Simple arg, right? Now people this way think. Z is a complex number 2 times cos. We'll write 225 plus I sine 225. People, can you tell me where is this complex number? This complex number is in the third quadrant. This complex number is in the third quadrant. 180 up to here, 225. This is the complex number. Then this 2. Then the line segment is this. Ending point is the point. By this point, we get what? The real part and imaginary part. In this case, when you see, the argument is that has exceeded the positive 180. That means the argument is not in the principal range. That's all right, never mind. Then in this case, when we write people arg of z, since this is not in the principal range, we write like this. Arg z equals 25 degrees like this. Now people, if we need to write this argument using the principal range, you can see we can't write that argument in the positive sense, because in the positive sense, the principal range but ends at 180. So then we have to go for this way, people. Right? Then this is 45 now, then this is 135, then minus 135. Then the same complex number you can write z equals 2 cos minus 135 plus I sine minus 135. This you can write. In this case, people, this 135 is in the principal range, even though that is negative argument. So then we can write in this case arg z, capital A we use, is what? Minus 135. But people, for both arguments, the location of the line segment which represents the complex number the same. That's the thing you have to understand in this case. Right. Come to this, people. Consider the complex number. Right? 2 times cos 225 plus I sine 225. Now draw this diagram. This is the positive sense, the angle, but that has exceeded the what? The principal range in the positive sense. If we need to keep that in the principal part, the argument in the principal part, then by positive angle we can't put that, because in the positive sense the principal part ends at 180. So then we have to come to this way, negative sense, up to minus 135. Right? You can understand that too. Right, people. Now we'll count a few questions here and then we go to the next part. Write down as an exercise, convert the following, write down, convert the following complex numbers to polar form. To polar form. Complex numbers to polar form. One plus I. And next one, minus 2. Wait for y. Minus 1 plus root 3i. Next one. And then minus 1 minus root 3i. Fourth one, people. Two minus 2. Right. We need to convert them to what? People, polar form now. We need to convert them to polar form. First one, people. Right. You can first write, yeah, this point. What is the people point correspond to this complex number? Real part 1, imaginary part 1 here. 1, 1, no. Right. Then in the first quadrant only, that line segment lies. Real axis, imaginary axis. Then this length we need, no, people. And this angle we need. Right. You can then very clearly see here. This is first in the first quadrant. This is 1. This is 1. This length is, people, what? Root 2, no? This length is root 2. Can you see the board? That is by Pythagoras theorem I directly obtained. And this angle you can write, people, tan theta. It's 1 by 1. It's 1. Theta pi by 4. Right? Then, people, we can write the polar form. How? It's a d equals, length is root 2, no, from here to here. Root 2 times cos 45 plus I sine 45. That means pi by 4. This is how we can write it. Like that we can write all three. Complex numbers convert into polar form. Right now? Right. Second one we'll take, number 2. -1 plus 3i. -1 is here, plus 3i here. Real part is -1, imaginary part is √3. So therefore, in the second quadrant, OP lies now. This is the people argument. It is still in the principal range. If I take this angle as alpha, people, what is tan alpha? Tan alpha. This height is √3 divided by, this is 1, √3 alpha 5/3. What is this length, people? 1 squared plus √3 squared root. That's 2, no? Right, this is 2. Then you can write Z equals 2. People, what angle we take? Not this one, no? Not this alpha. How do we define the argument? Argument is starting from the positive real axis in anticlockwise or clockwise. So this is the angle we now have to take now, theta. It is 2π/3. 2 times is it 6? No, that is 120. Cos 2π/3 plus I sine 2π/3. Like that we can write. Third one. We have this -1 minus √3i. Where is this quadrant, people? Third quadrant. This is -1. Minus √3i. This point, -1 minus √3, the coordinates form I'm writing, right? I'll take this as beta, people. This length as before 2 by using the Pythagoras theorem. Then we can write tan beta. It is √3/1. √3 beta is 5/3. So then you can write the complex number in this case using the principal argument. If you write, you get one answer. If not, you can keep this whole angle like this. This angle you can use. Then Z equals 2 times cos pi plus 5/3 plus I sine 5 plus 5/3. This is correct. Why, people? There is no rule given here. We have to keep this argument in principal range. If you need to keep this argument in the principal range, people, then the positive sense you can't go, because in the positive sense, the principal range ends at 180. Then we have to go this way. Oh, Z equals 2 times using principal range. minus 120 cos minus 2 pi by 3 plus I sine minus 2 pi by 3. Okay, this contains the argument in the principal range. Here, argument is in principal range. Principal range. Both are correct, people. But remember, if you are asked to write the complex number using the principal argument, don't keep this, you won't get marks. Because this argument is not in the principal range. If you're asked to write the argument in the principal range, people, definitely you have to put this answer. Right? Yeah. So come to the fourth one, 2 minus 2y. The corresponding quadrant is this. This x coordinate is 2, y coordinate is minus 2. This angle be gamma, tan gamma, you can write 2 by 2, it's 1, gamma 5 by 4. This length, what people? 2 root 2, no? 2 root 2. By using the Pythagoras theorem, 2 root 2. Then you can write. Well, if you use this one, never mind, we can write z equals 2 root 2 cos 2 pi minus pi by 4 plus I sine 2 pi minus pi by 4. Right. That we have put the argument using the positive sense, but not in the principal argument, because we are not asked to write that using the principal argument. If we are asked to write that in the principal argument, people, this is wrong, because after exceeding 180, in the positive sense, we don't have principal argument. So therefore, in that case, if we need to write in the principal argument, we can come to it like this. Or z equals 2 root 2. Right. This angle is now 45 now. Then from the real axis to reach this line, I have to rotate this way. Then when we rotate clockwise sense, people, that is negative. Right. Then we get cos minus pi by 4 plus I sine minus pi by 4. This is the one you have to keep for this z if you are asked to write that in principal argument. Understood? Right now? Right. That's what we did. Okay. Right, people. I think you could understand this well. Oh, anyhow, you little bit understood this, huh? Right. Okay, people, now we can come to the next one. Right. Right, people, now let's see, when we have a complex number, let's see how to find and mark the negative of that complex number. Right. And I'm going to take this example, people, to explain this easily. Suppose here z equals 1 plus I, the complex number. Its polar form, now I can write √2 cos pi by 4 plus I sin pi by 4. This one now, just before we did. People, now if I mark this complex number z on the Argand plane, 0.11 is the point on the Argand plane which represents the complex number z. This is now pi by 4. This is √2. Right. Now, people, I am going to take this one and I am going to find minus z. Therefore, you have to multiply the right hand side by minus sign. And you know, here we have this is 1, this is also 1. Then for this minus z, what is the point, people? Point going to be -1, -1. Point going to be -1, -1. That means, people, -1 means this same length I have take here. This length we have take here. Then such point is this. Then you can very clearly understand when we mark that point, this is the -1, -1. When we join that to this point O, you can see that line coming along this previous line we drew. This line I just now drew and the previous line being what, the same line. The reason you can explain, this height is 1, this also 1, then this angle is 45. This 45 and this 45 being equal means the vertical opposite angles are equal. Therefore, this should be the same line. Then this point represents, people, the complex number z. Then this point represents the complex number minus z. Then the length, this being equal to this. Now, people, you can very clearly understand on the Argand plane, by a line segment, a certain complex number z is represented. Then to find the minus z complex number, what you need to do is, people, the line segment that represents the complex number z, you have to reverse from the origin to the opposite direction. Right? You have to reverse the line segment from the origin. Okay. Or else, people, this line segment only represents the minus z, no. The line segment, this you have to rotate through an angle 180. Through an angle 180. Here, see, this line segment, when we rotate through an angle 180, you can see that comes onto this. Then, people, to get the negative complex number, what we need to do is the line segment that represents the complex number should be reversed from the origin. From the origin, not from the ending point. This same line segment you have to start to draw from the origin in the opposite direction so that this length and the new length being equal. Or else that line segment which represents z should be rotated about the origin. Okay, about the origin by an angle 180. That rotation part can easily be obtained, people, like this. Now I take this one. When I multiply that by minus, we get like this minus z minus √2 cos pi by 4 plus I sin pi by 4. People, remember with this figure, this is really the modulus. Modulus of a complex number, this place takes a modulus of a complex number. Modulus of a complex number, people, never be negative. Modulus means what? Length of the line segment? No, it is not negative. So then, therefore, we are not allowed to keep this minus sign here. We bring that inside. Then we have like this √2 minus cos pi by 4 plus I times minus sine pi by 4. This one we get. People, other thing is this. In the polar form, the standard form, remember, in the polar form, the standard form is z equals r cos theta plus I sin theta. This should be a positive quantity. And this cos theta figure coefficient should be positive 1. Sin theta coefficient should be positive y. Until you form that formation, people, you haven't expressed your complex number in the polar form. Then this is not the polar form, people, because this cos has negative, sin before has negative. Then this and this both should be positive. Then cos, sin both now at the moment negative. Cos, sin both negative, people, in the third quadrant. Okay. Therefore, we can find an angle for this cos and sin both to be negative. What is that? Pi plus pi by 4. This one you can write as how, people? Root 2 cos pi plus pi by 4 plus I sin pi plus pi by 4. This way you can write. And now you can see, people, the argument is not in the principal range. That is never mind. That is, of course, we won't worry about that. The argument in the positive sense is pi plus pi by 4. That is true now, people. Now up to here pi, this is pi by 4, pi plus pi by 4, right? That means, people, from the initial, it is located at a distance, at a length, at the angle pi by 4 with the real axis. No, then in order to reach this one, total angle is pi plus pi by 4. Another pi angle should be added. That means this line segment should be rotated about the point to by an angle pi. Then we get what? Negative complex number. Understand? Right? Yeah. Then write down, people, this way. To mark negative complex number on the Argand plane. To mark negative complex number on the Argand plane. To mark negative complex number on the Argand plane. Right. We'll write this way, people. One sentence. Right. Write down like this. Let z equals r cos theta plus I sin theta be a complex number, be a complex number on the Argand plane which is represented by point P. Point P. Point P. Real part, this imaginary part. Is it right? Right on. Now minus z equals minus r cos theta plus I sin theta. Then minus z equals r times minus cos theta plus I times minus sin theta. As I told you, minus signs can't be kept before sin and cos. Then we have to choose suitable angle there. R times, this is cos pi plus pi by 4 plus I sin pi plus pi by 4. Then you can very clearly see here that same length angle pi plus pi by 4 5 plus 5 by 4, how you do you get, people? 5 plus theta. You wrote this as theta. And then correct. 5 by 4, who wrote like this? 5 plus theta. Right. Now already we have angle theta. Another pi angle should be added. Then we have to rotate this way. All right. The same length these are. This is the minus z. Cp dash. This is pi now. Right, no? Okay. Right, well, then we'll write one sentence like this. Right, so then write down people like this. Therefore, minus z complex number can be obtained by rotating the line segment OP, about the point O by an angle pi. By an angle pi. O, write down O by reversing O by reversing the line segment OP starting from the origin O to the opposite direction. We get the position of minus z complex number. Minus z complex number. Right. People, I suppose here today enough. If I explain next year is taking time, I have to explain that, people. Otherwise, it is confusing. If at the beginning the theories get confused, it is very dangerous to work out questions. For the next theories, people, I must take some time because one by one taking countable examples I have to explain. So therefore, people, today I supposed to come to the end of the lesson here. Right? Any question here regarding the lesson?